Next up is going to be, we got Namrata from the University of Santa Cruz. And she's going to be talking about the Galactic-scale AGN driven winds in nearby elliptical galaxies. And you may start when you're ready.
Okay, thank you for the opportunity. Hi, I'm Namrata, and I shall be talking broadly about searching for maintenance mode feedback in typical quiescent galaxies. But more specifically, I shall focus on a sample of early type galaxies that we call red geysers that host galactic-scale AGN-driven winds. Right, so the question is, how do galaxies quench? So in this plot of redshift versus number density, we can see that the number of red and dead galaxies has been increasing steeply towards present time, which is redshift 0, which means that more and more galaxies are transitioning from the blue cloud towards the red sequence and are not going back. So now what is the cause of this quiescence? In the literature, the strongest proposition has been AGN feedback, specifically maintenance mode or radio mode feedback, where the central AGN, with the help of radio jets or winds or outflows, they suppress the star formation and keep it at a low level. But there has not been as many observational evidence of this sort of feedback in typical elliptical galaxies. And that is a context of my talk. Now, thanks to IFU surveys like MANGA, we now have spatially resolved information across thousands of galaxies. MANGA looks at nearby galaxies. And when we looked at all this enormous data, we found this sample of early type galaxies that show something like this. So here you are looking at the 2D spatially resolved H-alpha equivalent width map of an elliptical galaxy. So equivalent width is basically like flux. So you can think of this as the spatial distribution of warm ionized gas across the face of the galaxy. And you see this bisymmetric or biconical feature, which looks like a geyser or a fountain from the center. So that's why the name red geyser. And we have many examples of this in MANGA. So all of them show this bisymmetric or extended biconical feature in their ionized gas map. But if you look at the optical data or the optical image taken from SDSS, you can see that all of them are perfectly spheroidal. So they do not look, they do not show any peculiarity in them. So let's talk about some of the red geyser properties. They have the bisymmetric feature, which is the defining property. They are red and quiescent galaxies with no star formation, and they have lots of gas in them, both in the form of cool neutral gas, warm ionized gas, which can readily form which can readily just trigger star formation, but they don't. They also show very interesting kinematics. So the gas velocity value is very high compared to the stellar velocity. And they also show very clumpy and very high dispersion map. And this kinematics is actually where we got a lot of help from the Keck data, which is at a much higher spectral resolution. Finally, these galaxies also show low luminosity AGN at the center. And how do we know that? For that, we looked at the VLA first radio continuum data. And we found, I'm not going to the details, but we found that the red geyser sample, they show a much higher radio detection rate, as well as a much higher stacked radio flux value compared to the control sample that we constructed by matching in global properties. So again, the details are in this paper, but we concluded that these galaxies have low luminosity radio AGN in them with an average luminosity of about 10 to the 22 to 10 to the 23 watts per hertz. So now the main question is, so are these bisymmetric features that we are seeing in the gas, are these tracing galactic scale AGN driven winds? So for that, we look at the kinematics or the velocity. So this is what a 2D spatially resolved velocity field looks like in a red geyser. The major kinematic axis is always aligned with the bisymmetric feature. The values goes up to 250 to 300 kilometer per second. They show red shift on one side and the blue shift on the other with some occasional clumps here and there. They also show very high gas dispersion values, which goes upward of 220 kilometer per second. So the main question here is, can this velocity field be explained by radially outflowing gas particles entrained by the wind, if there is a wind? We constructed a very simple, we have a very simple toy wind model that has been described as Chung et al. And we actually found that a lot of this velocity maps can actually be explained or very well represented by this wind model. But again, we want to look at the more detailed kinematic signatures to kind of to be confirmed about this wind. So that is where the Keck data comes in. So we took the help of the ESI instrument, which gave us a spectral resolution of R of about 8,000, which is fourfold improvement than Munger's spectral resolution. So let us first talk about what we expect from our wind model. So this is a filled bicone. It is filled with warm gas clouds, which are emitting the emission lines. And each of these gas clouds are moving radially outward. So let's say the observer is standing here. So he will observe everything integrated along the line of sight. So let's say a spectra coming from the bottom would be integrated along the cone volume in the line of sight. And he will also observe the velocity to be projected along the line of sight. So a combination of this projection and integration should give rise to asymmetric emission lines. And not only that, the asymmetry should switch from one side to the other with a perfectly symmetrical spectra in the center, because there is not a lot of cone volume to integrate over in the center. It's totally because of the bicone geometry and the outflowing motion. So that's what we want to look at. So we put our Keck slit on top of this expected wind axis, and we extract spatially resolved spectra around each of these spatial bins of size 1 arcsecond. And this is what we saw. So I'm showing you the H alpha profiles at 2 different positions in the galaxy. And you can see, first of all, the lines are asymmetric. And the second thing is you can see the asymmetry going in the same direction as we predicted. So now showing you all the spectra along the slit. So the spectra from the bottom portion of the galaxy is shown in the bottommost row. And as you go up, the different rows show you the different spectra along the slit. And they're color coded by velocity. And you can see that the spectra in the blue shifted side has a red wing. They are all extended in the red part. And they become symmetric when you reach the center. And they start becoming asymmetry on the other side. So they have a blue wing. We also sampled the slightly off center to the wind cone to see what the line looked like. And we still see the asymmetry, but it's kind of harder to see. As you can imagine, the gas clouds are probably not entrained by the winds anymore because they are, this is sampling the age of the wind cone. We also took a slit along the center, and you can see that most of them show very symmetric line profile. The signal to noise goes down, becomes pretty bad at the edge because there is not a lot of gas there. But you can see that at least near the center, the lines are pretty symmetric. So in conclusion, the systematic asymmetry that we predicted from the cone model, it agrees very well with the observations, and we can say that the line asymmetries are consistent with wind hypothesis. So in conclusion, the red geysers are is a relatively common class of quiescent galaxies found at a rate of 5 to 8%. They show many interesting properties that I didn't have time to talk about, but they host low luminosity radio AGNs, and they show signatures of AGN-driven wind. Thank you.
Wonderful talk. We've got a couple of questions coming in. The first one is from Sarah White, and really it's a comment, lovely work at the start. And then the question is, can you use the kinematics to distinguish between an AGN wind or small flow power radio jets?
Okay, so I guess when I say winds and jets, I use them synonymously, but I would not expect them to have like very collimated like jets, because we do not actually see any jets in the radio. We see a continuum brightness from the center. But these are mostly, if you look at the Munger data, they mostly look at like a very broad kind of like feature. And when we fit our toy wind model, we found that the opening angles to be very broad. It's about like half angle is about 8 degrees or so. So that's where we are at this point. Okay.
Second question is, for clarification, what is the spatial extent of your outflows and radio emission?
So these are all, so these Munger's footprints are all like 20 arcsecond. So by spatial extent, it's almost the age of the galaxy. So Munger can look at the whole galaxy. These are all nearby galaxies. So Z about 0.05. So it's around like 20 kiloparsec or something like that.
And then one more question, but before we turn it over to Slack, do you see evidence for a change in ionization along the outflows?
So I didn't get to talk about them at all, but all these galaxies show extended liner-like emission. So they do not show, so we only looked at manga ionization. So the manga spatial resolution of about, it's not a lot, it's 2.5 arcsecond or something. So we see extended liner-like emission along those outflows, and there are occasional Seaford regions here and there. But I'm going to ask for more Keck time to look at this ionization in more detail.
All right, well, thank you very much.